Actually, it turned out that I was going a little too fast. But since yesterday's result was very important, I am going to go through some of the steps once again. Part of the problem also seems to be that the MSc students are not familiar with the four-dimensional notation, so which the others will be familiar with. So I am going to spend a little bit of time on that, not too much, and then we will proceed with today's step. What we started out with was the result for the Jacobi action, which we wrote as if I want to do the sum over the Jacobi action, okay, x of t, I. Let me write the Jacobi action explicitly. That was d lambda, let us say 0 to tau, square root of 2m e minus b dl. Okay, let me put a dl here, then I don't need this. I will just go in the path as the length of the path. Okay, this was the left hand side of the Jacobi action. This is the Jacobi action, exponential of that summed over all paths is what we are computing. This gives you the probability amplitude. Again, this notation confused a few people. This is an amplitude, not a probability. Okay, I just use P because there are only finite number of Greek letters. Okay, so the calligraphic P is supposed to say it is an amplitude. Okay. So it is the probability amplitude for a particle to go from x1 to x2 with an energy E. Then we showed that this can be related to integral 0 to infinity. Some is a time variable, but some dummy variable. E to the I E lambda of the original path vector, which is going from one end to another of exponential I. So this path integral is evaluated over some 0 to whatever is this time interval which is here. Let me call this as tau, just to be consistent with future notation. Tau 0 to tau d lambda of the quadratic path integral, which is half m g alpha beta x alpha dot x beta dot minus c. So let us again pause for a minute and make sure we understand that. Suppose you have a particle whose Lagrangian is half m, some kinetic energy term, which is g alpha beta x beta dot. And I told you that this could be, for example, because of r dot square plus r square theta dot square plus r square sin square theta phi dot square kind of form. That is how g alpha beta is doing here. Minus a potential energy and integrated between 0 to tau. This path integral will tell you what is the amplitude for a particle to go from a position x1 at lambda equals 0 to a position x2 at lambda equals tau. Okay, this is the standard path integral which we have been computing. This is a function of tau. Now if I do a Fourier transform of tau with respect to a variable e, that will give me the amplitude for the particle to go from x1 spatially to x2 spatial coordinates with an energy. That is precisely what is given here. Okay. So this is all we need. Now in order to get to the relativistic thing, we just want to make a few changes. The first, this is what apparently I went a little too rapidly, so let me do it slowly. The first thing we want to do is to say there is no potential. So this V goes away and the V goes away. Okay, so it's a free particle. That makes this integral to be just the length of the path, which is what we want finally for the case of a relativistic particle. Second thing we want to do is, now we want to think of all the four dimensions, time and space. So this g alpha beta I will write as g AB, and this I will write as A, this I will write as B. So my alpha beta went through 1, 2, 3. Now it goes 0, 1, 2, 3. So if you explicitly look at what this This is nothing but T dot square minus modulus of x dot square. Correct? Because we are using a signature convention plus minus minus minus. So that whole thing is written in this condensed notation. Then we will get the corresponding length interval here. But we would like to have the action for the free particle to be minus m times the dl. So in order to get that minus sign, I will just take a complex conjugate of the whole equation. So I get a minus I here. The original equation which I wrote down, I am just taking a complex conjugate. So this becomes minus I. Right? Then what do I need here? I need here just integral dl with a mass multiplier. So I will take e to be m by 2. So put for e m by 2. So that makes it just m. So put for e m by 2. Okay. So now we have reduced the left hand side exactly to the form we want. We want a summation over exponential minus I m dl, which is the action for a relativistic particle. So the left hand side is fine. Now let us look at the right hand side. Right hand side has this nice characterization that it is some path integral, quadratic path integral, with one energy type integration over. Okay. Now what is this? This is a quadratic path integral. We have done it several times. What will that give? That will give you m over 2 pi I, the time interval which is here tau, for each dimension, where you get plus sign here because I have put m here. So if you look at this, it is t dot square minus x dot square with an extra minus sign. So the x dot square part is perfectly the normal ordinary thing. So that would have given me 3 by 2 factor because 3 dimensions, so that would have given me a 3 by 2 factor. The time would have given me 4 by 2 provided the sign was the same. Because the sign is flipped with the square root, I get an extra I. So I get the result to be this with a square. This is the normalization. Then you will have exponential, the standard term, which is minus I m by 2. Here this will give me, let me write this explicitly, t2 minus t1 the whole square minus x2 minus x1 the whole square, the whole thing divided by the time interval tau. Okay. So already here I have started using what is known as the summation convention, that if the same index is repeated I am summing over. Here I will again make it more condensed. T2 minus T1 is what we call T, x2 minus x1 is what we call x. So this is t square minus x square, which I will just write as x square. Okay, x you think of as a 4 vector. So a notation like x square when I use, it stands for xa, which in turn stands for writing it as t square minus mod x square. Feel free to stop me if at any stage the notation becomes complicated. So we plug that in. So this entire expression became x square by tau. Then I just made a change in the variable. I called tau to be 2s. So I got this as integral 0 to infinity ds with an extra factor of 2 outside. Then I kept 1 m out. Okay, I need more space. I kept 1 m out. This I square gave me a minus sign, and so it was minus I. Then we kept 1 m in. It will be why this m is separated will become very obvious in a minute. Upon 16 pi square, because the star became 2s, that became 4 pi square is 16 pi square. Then that tau now becomes s square. Then you have exponential, this becomes minus I m s. Then we have minus I m by 4, because tau equal to s, x square by s. This is what we had in the last lecture, except for an overall constant c. Because I said that when you are doing this, because of dimensional reasons, it is good to keep a constant c here. So there was a constant c, which I wrote as 2cm. Okay. Now I want to, as I said, the rest of the lectures will go on exploring various properties of this. But I just want to write this in a slightly more sensible way, so that it will match with what everybody else is doing. This has to do with the dimensions. People usually choose this 2c in such a way that this 2cm becomes 1. That is, c is taken to be 1 over 2m. The point is that if you normally write down the kernel, what is the dimension of the kernel? The kernel is something which, if you take quantum mechanics, the kernel is something which is multiplied by the wave function, integrated over coordinates, and gives back the wave function. So the dimension of wave function goes out. So the kernel should have the dimensions of some inverse of the corresponding the product of the dimensions of the length. If it is in 3 dimensions, if you make a kernel, you will have some 1 upon that length cube kind of thing. So here it is conventional to take the kernel with a slightly different dimensions. So you don't want this extra cm hanging around. So we will choose this to be 1. It's just a choice. It has one nice consequence though. Once you have got this, suppose I change one more variable, that is I change s to sm. Okay? That is, I think of ms as a new variable. So I could have kept this as say s bar, just for convenience. Now think of s bar as becoming s upon s into m. That is, I put s bar equals ms. Then this will become m square. S bar is ms, so this m goes away. So if I put s bar as ms, I will get an extra m square here, that m will cancel with this. So you get the final answer in this form. This is the way every textbook will give, except that textbooks don't give this in this form, but they give it in some equivalent form. So it is minus I over 16 pi square integral 0 to infinity ds over s square e to the minus I m square s minus 1/4 x square by s. Now there is a reason, there is a slightly subtler reason why we made these choices. In non-relativistic mechanics, you almost never think of a mass zero particle. But when you do quantum field theory, the quanta of a field can be zero mass particle, like a photon or whatever. So we would like to do things in such a way that in the end, when you have a propagator, m equals 0 limit does not blow up in your face, and it has a nice limit. The moment you have written it like that, that is true, because I can take m going to 0 limit. All the overall constants has been settled in such a way that is why we keep an m square here. Okay. Though, as I said, it is nicer to keep this m and interpret that as the energy along the proper time, etc., etc. But this is a much more useful form of the experiment. Okay. Fine. Now let us start asking various questions about its properties. The first point, yeah.
So when you wrote down the original Jacobi action,
it had an
and you summed it over all the paths,
right.
The interpretation was that it's the ability to go from x1 to x2 with a fixed energy.
Okay.
But here this does not have, this is the full amplitude, right?
No, okay. In the non-relativistic case, we interpreted Jacobi action like this. Right. In the relativistic case, first of all, when you say it goes from x1 to x2, we are now talking about a even to even propagation. So it is going from t1 x1 to t2 x2. But it is going in some other time. That is the proper time, right? So what you would have got here, this object is analogous to your standard path integral kernel. It gives you the amplitude for a particle to go from x1 t1 to x2 t2 in a proper time now. Okay? Then I can say that with respect to the proper time, the energy is just m. So you say that it is going from one point to another, and I take a Fourier transform with respect to this proper time, which is what we did here, except for scaling and all that, and that energy we set it equal to m. So you can think of a amplitude. See, we don't care about the proper time. We want the amplitude for the particle to go from one event to another. So you first compute the amplitude for it to go from one event to another with its own clock showing a lapse of tau. Then you say, I don't care what its own clock is showing. So I would like to make sure that it had an energy mc square in its respect. So you would do a Fourier transform with that. So it's a very nice interpretation in that sense. You can actually think of it like a Jacobi reaction. Okay? Except that once you have done it, we will go around doing it for a mass zero particle or even a space-like separation, etc., where proper time may not make sense. Okay? But at least for the within the light cone, it has an answer.
So when you sum over all the arbitrary proper times that it could take,
yes,
you're still saying that it goes with an energy.
Yeah, that's right. That is the whole idea. Because see, this kernel has absolutely standard interpretation, right? Because this is just instead of 3 dimension, I am doing it in 4 dimension. But what you have to interpret is what is the star. So the star has to be thought of as the lapse of proper time as shown by its clock. But then you say, look, I don't care about that proper time. I want to integrate over that proper time. How do I integrate? The most natural integration is insisting that it had an energy equal to mc square with respect to that time, which is what we have done, and it gives you the correct result. Fine. So this is your final expression. The first point to note, as I said, this is the k1 function, and in fact, if you want to look at it, this is square root of x square k1 of I m square root of x square. Okay, it doesn't reveal much. Okay, but you can evaluate it in closed form. But let us look at the properties one after the other. We will do it slowly. The first thing is that it depends only on x square. This interval. That makes sense because first of all, by translation invariance of free particle, it can only depend on x. That is the separation between the coordinates of the two events. Second, Lorentz invariance tells you that there is only one quantity you can construct out of it, which is quadratic, since we are looking at the free particle, and therefore it depends only on x square. Okay. So that part is fine. Second, and a mildly shocking thing, which but I have sort of prepared you for this shock by interpreting it in a particular way, is that this quantity does not vanish outside the light cone. That is, if I draw a space-time diagram. This is space, this is time, and the particle is starting, suppose you want to know the amplitude for the particle to start from the origin and go to a point here. Okay, this is your x-axis. That amplitude is not zero. However, if you look at the properties of this, the properties of this function depends very crucially on whether the square root of x square is real or imaginary. See, square root of x square is square root of t square minus mod x square. So, if t is greater than mod x, you are in this region, then this is real. And if it is less, then you are in this region. And the properties depend crucially on that. And you can show, which we will do in a minute by another trick, that you can show that this entire propagator which we have obtained here, let me write it as x2, x1, it has the behavior e to the, let us say, plus or minus I m t, if you are looking at, let us say, x is equal to 0, and it goes as e to the minus m modulus of x, if you are looking at t is equal to 0. These are two convenient limits. What we are talking about is that if you go along this direction, it goes as e to the I m t kind of behavior. Okay? If you go along this direction, it goes as e to the minus m modulus of x. Why are these two directions important? We have already seen that this expression is Lorentz invariant. So if you take 2 points which are space-like connected, someone would have taught you in special relativity that I can make a Lorentz transformation and make them along this axis. That is, you can take away the time difference. There is always a frame in which t is equal to 0. Similarly, if you are in this domain, there is always a frame in which x is equal to 0. So that is what we have taken. So here it is oscillatory, but the moment you go outside the light cone, it falls exponentially. Again, it should not be a surprise. In the Jacobi action, we have seen that E greater than E less than B and E greater than B, there is a real and imaginary behavior. This is light tunneling. Classically, this propagation is forbidden. Quantum mechanically, it is not forbidden, but it comes with an exponentially small amplitude. Now, how do you see that? Of course, if you know Bessel functions, you can see that, but there is a easier way of seeing this in these sort of integrals. Since it's a good trick, it is good to learn this. I will put it in the practice problem. The idea is to use what is known as a saddle point integration. Okay? So, just for convenience, for a minute, assume that we have gone Euclidean. That essentially means these I factors are not there. There is an I. Yeah. These I factors are not there. So what you are looking at is an integral of e to the minus m square s. So you are looking at an integral of the following form. Integral 0 to infinity ds upon s square e to the minus m square s minus x square by 4s. How does this integral behave? When I think near s equals 0, it is not this is going to dominate. For large s, this is going to dominate. So this comes down with an exponential with a m square as the scale length, and this comes with an exponential with some 4 by x square as a scale length, right? So it is exponentially suppressed both near origin and near infinity. So it is very sharply peaked in between. Because it is very sharply peaked, you can expand this quantity as a Taylor series expansion about its maximum, and the leading order term will be dominated by the value at which this is the maximum. Now if you look at the maximum of this, you will find that that crucially depends on the sign of x square, because the maximum will be decided by m square equal to x square upon s square. So s square will come out as some square root, s will come out as some square root of x square. So that is how the square root of x square comes in, essentially. And if the dominant part, when you take the square root, you get something which is nice and real, then you get oscillatory behavior. Otherwise, you get the suppressed behavior. So if you do the integrals properly and get this and look at the asymptotic form, you will get at the same result. So the first result is that it doesn't die down outside the line. Okay. Now that already should tell you a few things, which we will take up in great detail when we look at the same thing in the Hamiltonian formulation. But just peeping ahead, let me show you. I'm teaching you in the notation all along. But suppose for a minute this can be expressed as some x2, some e to the minus I t, some Hamiltonian, some relativistic Hamiltonian, x1. We could do this for a non-relativistic particle. We don't know whether we can do it for a relativistic particle. It will turn out that we cannot. Okay? So this notation is misleading. It is not some x1 to x2. If it can be done, suppose this is some function. Lorentz invariance and translation invariance immediately tells you that this function can only depend on x square. Okay? Now, if this function does not vanish outside the electron, then this function is not zero when that is on the domain when not zero for the outside electron would be represented by x square, which is less than 0 in our notation. Okay? Suppose this f of x square does not vanish outside. And it will turn out that in most of the cases it will not. I mean, that is anything which you can think of, there will be a propagation amplitude outside. Then I can always choose my coordinate system in such a way that this corresponds to t is equal to 0. Therefore, I can put t is equal to 0 here. So you get the result that this is equal to x2, x1. Because when I take t is equal to 0, I do a Lorentz transformation. Whatever it is, everything has to be a Lorentz invariant. So when I take t is equal to 0, irrespective of the nature of the Hamiltonian, this quantity becomes x2, x1. This is a very strong result. The fact that it is not vanishing outside the electron implies that this x2, x1 cannot be 0 for x1 not equal to x2. This is in complete contradiction with what we have in non-relativistic case. So I told you at that time itself, this has to do with the locality of the particle. If a particle can be localized at x1, that is, what is it telling you? It is telling you the amplitude to find a particle at x2 after you have put it at x1. Okay? In non-relativistic quantum mechanics, this will be a Dirac-Delta function. So it will vanish for these two. In relativistic theory, this will, maybe already seen, this will go as e to the minus m modulus of x2 minus x1. So within one quantum wavelength, you cannot locate the particle, and that immediately follows for this. Okay? So this I told you that I will show you at some stage, and that is what is happening. And the correct interpretation for all this is what I showed you yesterday, that you think of paths which go backward and forward in time, and you think of it as some particle, antiparticles, etc., etc. I mean, we will make those interpretations more rigorous as we go along, but this is, as I said, is a sneak preview. Okay. Now let us go a bit further. I need some of these expressions, not all of them. So let me just rewrite this expression. I just need this. Okay. Now let us look at more properties of this. As I said, it's a horrible object to look at in real space. But if you do Fourier transform, things look better. So I want to first compute the Fourier transform of this quantity with respect to all the four coordinates. Okay. So before I do that, with a little bit of foresight, I will change this minus I m square s to minus I s m square minus I epsilon m square minus I epsilon, and of course I have e to the I by 4 x square by s. So this minus and minus cancels out. I into I will give me a minus sign, so that this epsilon makes sure it converges at the upper limit. Okay. This will turn out to be more important when we do inverse Fourier transform, but it is good to keep it here. So what I want to compute is the Fourier transform of this. So I want to compute integral d4 x x2 x1 e to the IPX Here the p is a 4-dimensional variable, just as our x was. So the notation being used here is p dot x with nothing below here. Stands for p0 x0, which is p0 t minus a momentum, 3 momentum p dot x. Okay. So p is a 4 vector. It has the components p0, px, py, pz. So p0, p dot x stands for this particular combination. So we are doing a Fourier transform of t and x with respect to p0 and p. Okay. So you do this, and also word on the notation. Our 3-dimensional Fourier transform notation was that we will always have some f of p e to the I p dot x, I believe this is what I used, times ddp kind of a thing upon 2 pi to the power d. This was the integration notation. Okay. So the spatial part should come with a plus sign in the f of p integration. So when I am doing a d3x integration, that should come with a minus sign, which is taken care of by giving a plus sign dx here. Fine. So we want to know what this quantity is. So this is given by plug it in and do the integral. So I have a minus I upon 16 pi square, going for a right, integral 0 to infinity ds over s square e to the minus is m square minus I epsilon. This much of it is not relevant for us. Then we are going to do a Fourier transform on this. So it will get multiplied by integral d4x e to the minus I by 4 x square by s plus ipx. Okay, now let me rub it down. Someone should have this expression. If we need it, we will just put it back. So what is this integral? So this is our usual Gaussian. So we might as well write it down. It is I over 16 pi square integral 0 to infinity ds upon s square yes m square minus my I epsilon. So the formula for this will involve first a pi divided by minus a, where a is the coefficient of this. So minus a here will be I, this whole thing, minus sign takes away, I is here and then 4 and then s goes on top. Okay. This has to come for every one of the integrals. The same sort of a thing. You have to remember that there is a sign flip here. So 3 of them will come with positive sign. So that for 3 of them there is no problem. Then the 4th one will have an extra minus sign. That just gives me a factor I. Okay. So this will be 2 and then I will have a factor I. So hopefully this is right. Then I have exponential minus b square. Minus b square will give me minus b square divided by 4a. So 4 times this. That is going to be again a minus sign. I by s, so s goes on top. So 1 minus and 1 minus cancels, and this will give me an I on top. So it is I p square s. This is what we have. So there is a minus sign which will go away with this minus sign. Then overall I seem to get an extra minus sign. Then 16 pi square will cancel with this, so that is all gone. So I get an integral 0 to infinity ds upon s square e to the minus is, okay, or rather e to the is p square minus m square minus is plus h. Let us stare at this result, assuming algebra is all correct, but algebra you can always check and correct a factor or whatever. So what I have done was this minus cancels with the square car minus, and then there is an extra I and an I which gave me this minus sign. Okay, so this is what I got. Okay, so what does this tell you? What?
S square
In the denominator.
in the numerator.
Okay, this is not there. This is not there because this s square cancels with this. Right, thanks. Okay, so this is what it is. So of course this is trivial, we integrate at one step, but I want to stop for a minute here. So what it tells you is that this entire result, this Fourier transform of this kernel, which I have written down, can be expressed in this form. Which means at this stage itself we can write the expression for x2, x1 in a, let me write it here, in a slightly different form. Because it is a Fourier transform, I can write the inverse Fourier transform x2, x1 as integral d4p divided by 2 pi to the power 4 e to the minus ipx, there I used a plus ipx, minus ipx. Then I can write down this entire expression, which I am going to write down with an integral in front, integral 0 to infinity ds. And what is left there is e to the is p square minus n square plus I epsilon. Okay. Now this should look a little bit familiar. See, what is happening here is that I have a d4p e to the minus ipx or some quantity here, which I can think of as some kind of a what is known as a super Hamiltonian. So let me write it down first and then I will explain. P is the momentum, and normally P is associated with I times the derivative with respect to coordinate. So the P square will become box in 4 dimension, because in 3 dimensional P square will become del square, right? So this will become a box. So suppose I look at the following expression. Take x2 e to the minus minus I yes box plus m square minus I epsilon x1. Just consider this expression and suppose I want to evaluate this expression. What I would have done is to put a complete set of momentum states here, and on that momentum state this would have just given me p square, thereby getting it, minus p square, thereby getting it back to this. Okay, this sign is taken care of. Then once the momentum state is given, that will give you a p x2 and a p x1, that would have given me this expression with an integration over d4. So this is equal to just integral 0 to infinity ds of this expression. Okay. So this is very nice because this looks as though I am working with a Hamiltonian, except that it is not 4-dimensional objects. A Hamiltonian which is of the form, looking at that, minus p square plus m square. Where did this Hamiltonian come from? Think of a Lagrangian which is minus 1/4 x dot square, which was what we were originally having, minus m square. See, if you think of where this expression came from, this 1/4 x square could have come from a Lagrangian with a kinetic energy minus 1/4 x dot square, and then you had this minus m square term. That comes from this. So right now we are back to classical mechanics. Think of a funny four-dimensional space with an extra lambda as the proper time, and these derivatives here represent derivatives with respect to lambda, and a Lagrangian which is like this. Once again, note on notation, when I say something like x dot square, just like these things, that corresponds to xa dot, which will translate to t dot square minus mod x dot square. Don't lose sight of this. So there are 4 coordinates here with respect to some internal time lambda. So that is the Lagrangian which you have here. So what will be the Hamiltonian corresponding to this? This is a Lagrangian. Normally you write it as m by 2. So if I take m to be half, this is the Lagrangian. So if it was m by 2, I know the Hamiltonian will have p square by 2m. When m becomes m by 2, then 2m just becomes unity. I'll get p square. And because it has a minus sign, it will have a minus sign. Then this is minus v that will get added. So this is the Lagrangian corresponding to this. This is exactly the Lagrangian we dealt with here. Right? So I want you to see the connections and the consistencies. If you think of a four-dimensional particle with this funny Lagrangian, and if you look at its corresponding Hamiltonian, this is what you will get. And this is going to become this operator, box plus m square. So you can already see roughly where fields and wave equations etc. can come from, because the box is a wave operator in 4 dimensions. Okay, but even though we are still doing particle dynamics here. Okay, fine. Now let us go back and do the last step of the integration. So this will give me, if I do the integral, 1 upon p square minus m square plus I epsilon and an I. So that I will take to the top and write it as I. This is the answer. Okay. So if I know this is the correct answer, but since it is contributed at a lower limit, I will pick up one extra minus sign. So we are missing one minus sign somewhere.
I guess exponential of I p square s will have a minus sign.
Where? This one?
No. There is a step out. I p there.
Yes, here? No, this is I p square s.
It should have minus sign.
No, that is the correct sign, because it should come with p square minus m square. So it may have to do with this extra minus I which I put here, but this we will verify. Don't worry about that. So there is some sign issue here. I think it should be I over p square minus m square plus epsilon rather than minus I, but we will sort it out. So let me just look at this expression for the moment. What does it tell you? Yeah.
Like when you take that, you have extra I coming out, right?
Yeah.
There was a minus sign with the p square, as in the when you take the Gaussian.
Gaussian, right?
But how will you decide whether you take I or minus sign over? As in it is a.
Okay, that could be the reason. So I think I took the I should have taken minus I. That's correct. You have got it. No, the way you decide is by putting the thing in the Euclidean sector and continuing it back. That is one way of doing it. Otherwise, you look at where the i's go and put it properly. Okay. So either one of them would have given you the reason, and that would be the reason that I missed this I. Okay. We will check that. So finally, so this I think when you do this should have been minus sign, and that is where the changes occur. Okay. So let us sort this out. You sort it out. Okay. So you get the final answer to be this, and the answer here has a 1 upon p square minus m square plus I So what does this mean? What it is giving you here is that even though the original propagator to go from x1 to x2 was a Hankel function, if you look at the propagator in the momentum space, the expression is remarkably simple. It is just I over p square minus m square plus I epsilon. So the momentum space propagator is just this. Okay. And the pole of the propagator tells you the actual dispersion relation for the particles. Okay, p square will be the pole of the propagator except for the I epsilon occurs at p square is equal to m square. Okay, which is where the particles energy and momentum are related by exactly that condition. Now this denominator is precisely the kind of denominator we got even in non-relative physics. Because in the non-relative physics I showed you that if you take a Fourier transform with respect to the spatial coordinates, you get 1 upon energy minus p square by 2m plus I epsilon. This is the relativistic analog of that. And once again showing that it is a mathematical structure is exactly the same. Now this propagator we will keep using. This is called the Feynman propagator in the momentum space, and this is what we will use in all the perturbation theory, etc. It's a very important object. Okay. Now I want to do one more thing. I want to evaluate the Fourier transform, not over the 4-dimensional P, but over the 3-dimensional P. So let us do that. And there's a reason for that. You can obtain it from this. Let us do it independently. So we again work with this quantity, which is, so what we want to now do is to do a d3x integration of e to the minus I p dot x x2 x4. Okay. How do we do this? Same thing. You go on substituting for that in an integral form. Integral 0 to infinity ds upon s square, and I think we had the coefficient as minus I upon 16 pi square, if I remember right. E to the minus I s m square minus I epsilon. This whole thing is multiplied by the part where we need the integral. But here actually I can take one more factor out. The time doesn't contribute. So it is e to the minus I by 4s into, there is a t square minus x square. So I am keeping the t square there. Then I have integral over d3x e to the I p dot x minus p dot x. Exponential, this minus will go away now, plus I mod x square upon 4s. Okay, so this is again the same kind of a Gaussian. This integral is going to give us pi over, this is a factor now, which is going to be I 4 pi s to the power 3 by 2. There are only 3 integrals. Then exponential minus b square. B square will give me minus p square upon 4 times a, which is I upon 4s. So I is the denominator and an s. This will give me a minus I s p square. That should tally with this. Here we got plus, but this p square had a p naught square minus p square, and that's what we have got. So this is what we have. So we have to now do this a little bit more carefully. So not everything will cancel out. I have an integral 0 to infinity ds. I have a 1 by s square and an s to the 3 by 2. So it is ds upon root s. Then I have a 16 pi square here, which is 4 pi the whole square. And then I have a 4 pi to the 3 by 2. So it is 1 upon square root of 4 pi, that is 2 root pi. So I have taken care of this 4 pi, I have taken care of this, I have taken care of this s factors. Then I have an I to the 3 by 2, that is 1 I and 1 root I. So let us keep the I and let us keep the root I. So I will have a root pi into I. Then I have an extra factor of I which will cancel with this and give me a minus 1. So again, I am not very sure about the algebra, but that those things we can check. So this much we have. And what is left now is e to the minus I t square by 4s, which comes from that, and a minus is omega p square minus is square. What I have done is that I have a minus is m square and a minus is p square. I have added them up and defined a quantity omega p square, which is p square plus m square. This is just the energy. Omega is just the energy, because square root of p square plus m square gives you the energy of the particle, and that is what you have got. So this is the integral which I want to perform. I have a ds integral too. Okay. So the natural substitution is some s is equal to, let us say, rho square. Then I will get rho here. S is rho square, so there is a 2 rho d rho. 2 goes, rho goes, and I just have a d rho. This s becomes rho square. This s becomes rho square. Okay. So you are left with an integral 0 to infinity of something which is an exponential upon rho square and an exponential rho square. Now it turns out that this has a closed form. So I will write down the result here. This is again an exercise for you to do. Integral 0 to infinity dx of e to the ax square plus b by x square is equal to half the standard factor pi over minus a to the power half. Then you get a e to the minus 2 square root of a. This is actually a nice integral, and there is a very cute trick to evaluate it. So I will leave it you to have fun. You can of course look it up. I mean, this is the thing. And it is up to you to make sure the integral converges. So I just put a and b here. That should have suitable signs and things like that. So this is what we are going to use. So what will happen is that you have a minus 1 over root pi I. Let it be there. So when I do this, I am going to again pick up pi upon minus a. So a is the coefficient of this. So minus a will be I, and a 4 t square. Sorry, 4 and a t square is the denominator. Let me make sure. So this is the, I am integrating, sorry, this is the coefficient of the other one. I am integrating over rho, so it is pi over minus a is this quantity. Okay. Minus a will take care of this factor, and I have an I, and then omega p square. Here I don't have to worry about epsilon. So that takes care of the prefactor and a factor half 2 from this factor half. Then exponential minus 2 square root of AB. Square root of AB will be this minus and this minus will give me a minus sign. I into I will give me another minus sign, so that I don't have to worry about. So the coefficients will be t square by 4. And here the coefficient will be omega p square to the power half. Okay, let me see whether I got the prefactor right. So there is a root pi and a root pi which will go away. Then there is a square root of I and a square root of I. That will give me an I. Yeah, square root of I into square root of I will give me an I. So I will get an I on top. I'm not sure about that factor, but that is alright. So that will give me an I on top. And this will give me an omega. So what you get is 1 upon 2 omega p. I have missed one I factor somewhere. Ah, that is right. That is from this. I into I with a minus sign, so this is correct. Okay. So in this 2, 4 and this 2 will go away, and you are left with this. Up to this, everything is fine. At this stage, you should resist the temptation to write the square root as omega pt. It is omega p modulus of t, and that makes all the difference. So the answer is 1 over 2 omega p e to the minus. Oh, there is another. Here is another. E to the minus I omega p modulus. Okay. What does that mean? So now let us get back to this. What we have proved, just writing down the first line and the last line, is that integral over d3x of x2, x1 e to the minus I p dot x is given by 1 over 2 omega p e to the minus I omega p modulus. If you recall, very long back, we did the same thing for the non-relativistic propagator. This is for the relativistic propagator. Okay? In the non-relativistic case, the corresponding result was e to the minus I omega p times just t. This was the non-relativistic case with a theta of t. Okay? And I show, yeah. Mod t. Mod t comes because I am taking t squared square root. Whether t is positive or t is negative, t square is the same. Therefore, square root of t square is always mod t. Okay? Yeah. There is normally square root of t square you will write as t, but that is wrong because when t changes sign it will reflect. So it is modulus of t. In this particular case, it turns out to be crucial. Now, the reason it is crucial is because, for one thing, your final answer should only depend on x square minus, the original kernel was depending only on x square minus t square. So, t going to minus t was an invariance. So, if you did only a spatial Fourier transform, leaving time alone, the final answer again should be invariant under t going to minus t. So if you didn't take care of that, you are doing something wrong. So this was the main difference between the relativistic and non-relativistic case. And that makes several crucial differences. In particular, we proved a theorem that this x2 to x1 propagator will be transitive. Just using the transitivity, translational and meaning, we proved a theorem that its Fourier transform should have this power. Okay, with nothing else in front. Theta of t, in some sense, if you are thinking of t2 greater than t1, that doesn't matter, but there can't be anything in front. Here you do pick up this 1 upon 2 omega p, as a result of which this is not transitive. It may look very, very innocuous. After all, there is just an 1 over 2 omega p, and how can it make all these difference? It will make all that difference. And we will see later that this 1 over 2 omega p has an extremely important physical reason to be there. Okay. So this result is actually nicer, because now I can write the propagator x2, x1. Instead of that 4-dimensional form, I could have now written this as to an inverse Fourier transform. It is integral over d3p upon 2 pi d whole cube e to the I p dot x upon 2 omega p times this e to the minus modulus of this, that can be written as theta of t e to the minus I omega p t plus theta of minus t e to the I omega p t. This is just expanding out the modulus. When t is positive, it is just e to the minus I omega pt. If t is negative, see, theta function picks up the sign depending on the sign of the argument. Theta of minus t, it will be e to the I omega pt, because modulus of t is minus t for negative t. Okay? So this is the final closed form for the propagator, which is much nicer than the original form which we have. And it tells you something important. Suppose you are looking at t greater than 0, then it tells you the propagation is coming out of e to the I p dot x minus I omega pt. And something which we have to understand and relate to. This is the energy, this is the momentum, and this is the way it is propagated. But if t is less than 0, if it is negative, then the sign of the energy gets split. So there are positive energy modes which are propagating forward in time, and negative energy modes which are propagating backward. So when you think in terms of some modes, I mean, if you think of a relativistic particle as having a energy which is p square plus m square, this tells you that yes, omega p square is p square plus m square, but omega p can be either plus that quantity or minus that quantity. And in the propagation, the positive energy modes go forward in time, and the negative energy modes go backward. And that we could immediately get by doing that one Fourier transform. Now let us do this a little bit greater detail. I will now write this as d3p upon 2 pi d whole cube 1 upon 2 omega p. This much I would like to keep together. Then I will take theta of t times e to the minus I px, because this is, if I take a minus I out, this is omega t and a p dot x. So if I think of a 4 vector whose time component is energy, the momentum 4 vector whose time component is the energy and the 3 spatial components are the momentum, this is just a 4 vector dot product which I wrote down here. Okay, except that p naught is now identified with omega p. So that is what this is. Now let us look at the other one. In the second term, we will play a trick. What we will do is to just take the second term, because it is sum of 2 terms. Look at the second term. In the second term, we will flip the sign of p. So if I flip the sign of p, this is just a dummy variable which is being integrated. Fortunately, omega p does not change sign. So I'll have a minus sign here. So I can use it with a minus sign. So this comes out to be plus theta of minus t e to the IPX. So this is a nice relativistically invariant way in which you can write this. Except for this factor which we want to understand. Where did this 1 upon 2 omega p come? That is necessary because in relativistic theory, if things are relativistically invariant, you should always have that factor with the momentum integral. So let me explain where that comes from. In three-dimensional space, when you do the integrals d3x and d3p, you can work with. In 4 dimensions, when you are doing an integral over distribution function for particles, etc., the Lorentz invariant integral which you will have will be something like d4p. Okay, suppose there is some distribution function for particles or whatever. When you do this d4p integration, you want to ensure that the p square is equal to m square for the particle. See, you can't integrate over the zero component and special component completely arbitrarily when you are talking about real particles. So if you get a set of real particles and you do this kind of an integral, this is what you will be doing. Now this integral over anything you write here is manifestly Lorentz invariant, because this is Lorentz invariant and this is Lorentz invariant, right? So let us write this down as integral over d3p and an integral over dp0. So this d4p I am separating it out. Then the Dirac delta function I want to write as p0 square minus modulus of p square plus m square, which is this omega p. Okay. So this is just separating this out into p naught square minus mod p square and adding up mod p square with m square to call it omega p. So this is exactly the same integral as that. Since this is Lorentz invariant, this is also Lorentz invariant, and whatever I am putting here is supposed to be Lorentz invariant. This integral can be evaluated, because if you are going to suppose you had some function here which dependent on p0 and p independently, that is how you would have done this integral, and that is the function which is sitting here, the function of p0 and p. What this Dirac delta function tells you is that this p0 should be set equal to this, and we will also assume there is a theta of p naught, that only positive value of omega p is picked up for real particles. Think of this as like a distribution function. So when you do this, you want to convert this Dirac delta function. So there is a rule for it. There is a rule which says that Dirac delta function of some function of x can be thought of as Dirac delta function of the roots where f of x vanishes, which I will call x over xi, 1 upon f prime evaluated at that xi modulus summed over all roots. Now in case you don't know, let us spend for a minute. What is a Dirac delta function? The Dirac delta function is 0 everywhere except when the argument of the Dirac delta function vanishes. Okay? So this Dirac delta function is going to do anything non-trivial only when f of x vanishes. So you first put f of x equals 0. In general, that can have several roots. F of x as an arbitrary function can vanish at several points. So call them x1, x2, x3, xn. And each of those points, Dirac delta function is going to do something. So you put a Dirac delta function on that x minus xi. But you need to keep this f prime of xi, because the Dirac delta functions are normalized by saying this integral over df of Dirac delta function of f would be unity. So you have to write this as df by dx into dx when you are converting into x. This is your f prime, and that f prime has to cancel this f prime. in order to make sure that this integral over this gives you 1. Okay? So this is a formula, and that formula we are going to use here. When you use here, this is your function. This is a function of P naught. So you take the derivative of this function with respect to P naught. That will give you 2P naught, and that you have to put at the denominator. So you have a 2P naught modulus in the denominator times derived as a function of P naught minus omega p. Okay? There is another root, but we are only taking the positive root for real physical body. So now when you integrate this whole thing, what it tells you is that you can evaluate this integral by doing integral d3p. This p naught with this derived derivative function tells you it takes value only on omega p. And it is positive, so modulus sign is not needed. 2 omega p times, this is already now taken care of, the P naught integral has been performed. F of P naught set equal to the physical value omega p. Okay? The whole point is that since we started out with a relativistically Lorentz invariant integral, and since this is supposed to be invariant, this has to be Lorentz invariant. That is what we need. In any integration over momentum, hereafter whenever we are doing these sort of things, you will find very naturally that this integral will come. Because the left hand side is Lorentz invariant and everything else is Lorentz invariant. Take T2 greater than T1. So e to the ATX is Lorentz invariant. This has to be Lorentz invariant to maintain Lorentz invariant non-dependence. So this 1 over 2 omega p, which we were annoyed with here, comes for a very important reason. You could not have got out of it. When I do the inverse Fourier transform, it has to give me a Lorentz invariant result. So the maths knows that, and it will give you that 1 over 2 omega. Okay. So this is our first indication that when you are looking at this propagator, not only that it is outside the light cone, it is outside the light cone because it is going forward and backward. When it does that, there is a backward propagation and forward propagation, and they are taken care of. Okay. This also tells you immediately that you could not have written it as a x2, x1 matrix element of a Hamiltonian. Because what would you do? The Hamiltonian should have, being a relativistic particle, it should have an energy eigenvalue which is either omega p or minus omega p. I am not even saying that we should not have negative energy solutions or any such thing. The Hamiltonian eigenvalues will be either omega p or minus omega p. But you have to take both of them into account. Just one of them will not do. And if you are taking both of them into account, you will not pick up these correct factors. There is one going forward in time and the other going backward. And that is the reason why ultimately this notation is a bad notation. It is not going from any x2 to x1. It is a single function of x2 comma x1. Okay? But I sort of started with this in non-relativistic case and I continued with that. Okay. So we have now done two kinds of integration. One is we have done the full 4-dimensional integration and we got 1 over p square minus m square plus I epsilon. Then we have done a 3-dimensional momentum integration and we got 1 upon this quantity. Now of course if I do an inverse transformation from the 4-dimensional integral, I should be able to get back this. And that is going to be again important because that will teach us how to do things like analytic continuation in that momentum space. So I think I will stop here. I was thinking of taking a class tomorrow, but it turns out that this room is occupied, and also this week we had fairly heavy amount of material, so I won't do it this Friday. We will compensate for it some other time. And anyway, most of the classes we are overshooting by 10 minutes, 15 minutes kind of. So that is not an issue. So any questions on this? We'll stop here. Yeah.
Could you repeat the argument where you said that there is a negative energy space?
This one? Okay. So, by convention, if you think of non-relativistic particles or whatever, e to the minus it, this coefficient is the energy. Okay? And omega p, again by convention, is a positive quantity. That is, we are thinking of omega p as the positive square root of this. So, this represents a positive energy mode. if I just think of t greater than 0, then what I get is e to the I p dot x minus I omega t integrated over t3. And this is a very nice and natural quantity for me to have, because just from non-relativistic physics, if you start with a particle which is propagating, if I decompose it into momentum modes, the momentum p will come with an energy which is equal to this. What it tells you is that there is another piece. Okay? The another piece has exactly the opposite sign in the phase. So I can think of this as minus of omega p with an extra minus sign. That is, put a minus sign here and write minus omega p. So this is like a negative energy mode which is propagated, and that kicks in only when t is negative. So does it answer your question, or is there something else which you want? Yeah. What is the confusion? Let's see whether
So
sorry.
T there, like, it is 3 dot minus t.
Yes.
And we are taking t to go, t to increase.
No, you think of any t is the difference between t2 and t1. See, the left hand side is a function of x2, x1, which is a function of t2 and t1. So let us just concentrate on t2 and t1. So I could have evaluated this function for t2 greater than t1 or t2 less than t1. So what I am now legitimately allowed to do is to take a space-time diagram like this. This is x, this is t. Take some point here which corresponds to x1 t1. Then I want to know what is the amplitude for the particle to go here. So this is your t1, this is your t2, and t2 is less than t1. If you are going to do everything by a nice causal propagation, I wouldn't ask this question. In non-relativistic mechanics, I don't ask this question. I say that amplitude is 0. Things don't go backward in time. So I would have said that is 0, but in relativistic mechanics, this is not 0. I can't set it to 0 because when I computed the path integral, I got an answer, which when I try to reinterpret in Fourier space, tells you that if these are the 2 points you are considering, then this is not going to contribute. Only this is going to contribute. This is 1, and the answer is given with e to the I omega pt, where omega p is positive. Okay. So that I cannot interpret in any way other than by saying that is a negative energy mode which is propagated. Of course, we will eventually see that the moment you go to field theory, this negative energy, positive energy, etc., you don't have to worry about, and you can always think of everything propagating forward in time. But you need to have particles and antiparticles. So in fact, that is the greatest results from combining special relativity with quantum mechanics. It tells you that to every particle there is an antiparticle. This is the strong result. Because the things like, the number of particles is not conserved and particles get created and annihilated, these things happen even in second quantized pictures. Like if you have phonons can be created and destroyed. But you never think in terms of particle-antiparticle pairs there. And that is the new effect which the relativity brings. Now one more thing is, I also told you about this paraxial optics analogy in one of the classes, that if you take a wave equation and you are only propagating forward in one direction, which is the paraxial optics limit, and you suppress the backward propagation and sideways propagation, then you end up getting a result which is very similar to the non-relativistic propagator. And at that time I told you that the exact result would have been something like a relativistic propagator. That is what we are seeing here. Because here we are not saying things are propagating only forward in time. It is forwarding both forward and back. Yeah.
Like when you have this propagator,
Yeah.
like how are you supposed to take a non-relativistic limit of it?
Okay, I'm going to do this at some stage. But essentially what will happen is that you will find that the two terms which you have, one of them will have a e to the minus imc square t, and other will have e to the plus imc square t. In the non-relativistic limit, that is the leading term. And you can pull out that e to the minus imc square t, and the remaining things will give you the correct limit. I'll try to do that in one of the classes, or throw it in as an exercise, but that is doable. You can take the full propagator here, You can even do a saddle point approximation on that and then take C going to infinity limit. You will recover the non-relativistic propagator except for this minus mc square t. Okay, that is not to be treated lightly, but most people do that. If you just throw away that e to the minus imc square t, then the remaining part is exactly the non-relativistic.
From the non-relativistic limit, when we had the propagator before, right?
Yeah.
So in space-like interval, you had an e raised to minus n.
Correct. Correct.
But there, I don't see how you would take the non-relativistic limit.
But that is not an issue, right? Because in the Newtonian non-relativistic limit, there is no space-like and time-like intervals. You can go from any point to any point. So that problem never arises. You get the expression, and that is, you can go on the space-like coordinate. So all these extra factors are dependent on C. Like when you say e to the minus m times something, it is h cross over mc. So m comes as mc. When C goes to infinity, that term will just go to 0. And your light cone sort of spreads. Things can propagate at infinity. Any other?
So we did all this and you realized that okay, x1, x2 is not to be interpreted the way you were interpreting it.
Yes.
So now what does
Yes, then I need a few more lectures. So what I will show is that there is a natural way. We haven't explored all the mysteries of this propagator. It's a very beautiful object. We have only sort of touched the iceberg. We will rewrite it in another way. Then it will turn out that this can be related to a bunch of harmonic oscillators, and you can actually construct a field out of it. And then we will interpret everything in terms of fields with particles and antiparticles. So that will take a few more classes. Maybe 2 more, yeah.
So in that case, I'm just asking.
Yeah.
Will it mean that okay, this is the amplitude for a particle to propagate from one point to the other point, or because that's the
because you need to be very careful how you are interpreting it operationally. That is what quantum mechanics always told you, and relativity adds a new dimension to it. Ultimately, after you do whatever you want with quantum field theory and everything, Feynman propagator will not vanish outside the light cone. And you take any standard textbook, there is an expression for Feynman propagator that will not vanish outside the light cone. That means if I put a particle here, I create a particle in some place, then the amplitude for you to find that particle outside the light cone is non-zero. It's very tiny, but it is non-zero. All that field theory is going to do is to reinterpret it by saying that there is a particle-antiparticle which are produced, which are all inside the light cone processes. 2 of them has cancelled out and the other one is going back. That is how we will interpret it. So we will see that the momentum eigenstates continue to be good eigenstates, while the position eigenstates is not such a good eigenstate. That is what we will see. Any other? Yeah.
Given the clear form of the position storage one, where we consider the mod of the
Mod T. Yeah.
So there, why don't we think about mod omega p?
Mod omega p. Oh, that is just a question of notation. What I am writing as omega p is actually mod omega p. See, I am defining omega to be p to be the positive square root of p square plus n square. But I can't define t to be the positive square root of t square. Right? Because t is a variable. Omega p is a constant. I mean, for a given momentum, it is the energy which we are talking about. So that is why I have explicitly omega p and the minus omega p in these 2 terms. Okay, I am taking them step by step. While in modulus of t, the reason is that when you take square root of t square, if I write it as t, I am doing something wrong because the left hand side is invariant under t going to minus t. So the right hand side has to be invariant under t going to minus t. So it has to be a modulus.
Well, in omega p, that's not the case.
No, in omega p by definition is a positive quantity. Okay, when I need to take a negative square root, I will put a minus sign explicitly.
So thereby saying that, are we saying that omega p can be negative?
No, the symbol omega p can never be negative because I had defined it to be plus square root p square plus n square. Okay, so that symbol is never negative. But when I need to work with a minus square root of p square plus m square, I will write it as minus omega. It's just a notation. Anything else? Okay.